This is the third part of our discussion on the concept of limit of complex valued functions. So far, we have given a precise mathematical definition of limit of a complex valued function. And then we described a relation between the limits of a complex valued function and limits of multivariable real valued functions. We used this connection to solve some simple examples. So in this discussion, we are going to prove that result. So far, we have seen that if complex valued function can be written in this form, u of xy plus iota v of xy, and with these notations, we can state the following result. So this function has limit u naught plus iota v naught as z approaches to z naught if and only if the limit xy approaches to x naught y naught of u of xy is u naught and the limit xy approaches to x naught y naught of v of xy is v naught. Now what does this if and only if means, or if means? So it is also described as necessary and sufficient condition. So it means that these two statements, these two mathematical statements are in fact logically equivalent. So they are necessary and sufficient to each other. So if this holds, so for example, if this statement holds, if this is true, then we should be able to prove using some simple steps that this statement is also true. And if this statement, the second statement, is true, then using some simple steps, we should be able to prove that this first statement is also true. So they are logically equivalent to each other. And assuming that first statement is true is equivalent to assuming that the second statement is true, and vice versa. Okay, so of course, the way we are going to prove this result is based on the definition of this if and only if. So it means we are going to first assume that this first statement is true. In other words, the complex limit of this complex valued function is u naught plus iota v naught, and then we are going to prove these two statements, or we are going to prove that these two limits are u naught and v naught. Okay. Of course, when we say that this limit exists, then it means that it satisfies the definition of limit of a complex valued function that we have discussed in our earlier discussions. So let's see what was that precise definition. It means that for every epsilon, epsilon is arbitrary, there exists a delta. Delta is a function of epsilon such that the distance between these functional values is less than epsilon whenever we are in the delta neighborhood in this punctured disk of radius epsilon and center z naught. And what do we want to show? We want to show that limit xy approaches to x naught y naught of u of xy is u naught and limit xy approaches to x naught y naught of v of xy is v naught. Now u of xy and v of xy, so these are real valued functions of two variables, and we should be, so if we want to prove this thing, then we should be using the definition that we described in our earlier discussions about the limits of real valued functions. Okay, so this was the definition. So if this limit is equal to u naught, it means for every epsilon greater than 0, there should exist a delta such that the distance between the functional values and u naught is less than epsilon whenever the distance between xy and x naught y naught is less than delta. So these are our basic definitions. Okay, so in other words, whenever I'm saying that this limit exists, it means that it satisfies the definition which we described earlier. And similarly, if we want to prove this thing, we should be proving that this limit satisfies this condition. Okay, so let's start with our proof. So it is given that this limit is equal to u naught plus v naught. So this implies this is our given statement. Okay, so this is the fact, and we can use this fact in our proof. Okay, so what is given? For epsilon greater than 0, there exists delta greater than 0 such that Okay, so the distance between f of z, so I'm going to use its expanded notation. So in other words, u of xy plus iota v of xy minus this limit u naught plus iota v naught is less than epsilon whenever the distance between, this is z naught, so let's say this is z naught, so z minus z naught is less than delta and of course greater than 0. Okay, so this is the given statement. This is true. For every epsilon we can find a delta. Okay, so we can use this statement. Okay, so now we can write it down in the following way. So logically equivalent to the following statement. So I'm going to ignore this xy just to simplify the steps. So u minus u naught plus iota v minus v naught less than epsilon whenever this x minus x naught plus iota y minus y naught is less than delta. So this is given. We are allowed to use this thing. Now let's see what do we want to prove. Okay, so we want to prove that this limit xy approaches to x naught y naught of u of xy is equal to u naught. Okay, so that means that for epsilon greater than 0, so now this is the statement that we want to prove. Okay, so we want to show this thing. For epsilon greater than 0, we want to find this delta greater than 0 such that the distance between, so once again I am ignoring this x and y variables, so u minus u naught is less than epsilon whenever the distance between this xy, okay, so the distance between x plus iota y and x naught plus iota y naught is less than delta and of course greater than 0. So that is the statement that we want to show. Now what are we allowed to use? We are allowed to use only this part. These are the facts. And what do we want to prove? So we want to prove these things. So for epsilon greater than 0, we should be able to find this delta. Now let's see how do we prove this thing. So using the observation that u minus u naught is less than or equal to u minus u naught plus iota v minus v naught. Okay, so and similarly v minus v naught is less than or equal to u minus u naught plus iota v minus v naught. So using this observation we can easily prove our statement. Okay, so since let's start from the first step. So u minus u naught, we want to prove that this is less than epsilon. So this is less than or equal to, so this statement is in fact f of z minus z naught. Okay, so in other words this becomes f of z minus z naught. So this is less than epsilon whenever z minus z naught is less than delta and of course greater than 0. So basically we are using the definition of the limit of this complex valued function. Since the limit of f of z is z naught, so that's why this is less than epsilon whenever this distance is less than delta, and this implies that the distance between u naught and u is less than epsilon. So this implies u minus u naught is less than epsilon whenever the distance between z and z naught is less than delta. Okay, so similarly we can prove that. Similarly we can prove this thing for V and V naught. So V minus V naught is less than epsilon whenever the distance between Z and Z naught is less than delta. Okay. So there is a simple point over here that of course if we want to prove that the limit of u is u naught, then we start from here. We choose our epsilon in this case, and then we go to the definition of the limit of complex valued function, that okay, the limit of f of z is z naught, so that's why for this epsilon there should exist a delta. So more precisely, we are going in the opposite way. Okay, so if we want to prove that the limit of u is u naught, then we choose epsilon over here and we need to find delta, and for this particular epsilon we find delta corresponding to the limit of f of z is z naught, and then we use that delta over here. Okay. Now let's assume this second part and we want to prove this first part. Okay, so far we have assumed that this part is true. If this part is true, then this part is also true. Now we want to prove the converse of this thing, that if these two limits exist and are equal to u naught v naught, then the limit of this complex valued function is u naught plus v naught. Okay, so let's see if these are the limits, then what does it mean? So what is given? So given is for epsilon greater than 0, there exists delta greater than 0 such that, okay, so the distance between u and u naught, so once again I'm ignoring this x and y variable just to simplify the writing, is less than epsilon whenever the distance between z and z naught is less than delta. Now this z is xy and this z naught is x naught y naught, or if you want to use the other notations, then the distance between ordered pair xy and ordered pair x naught y naught is less than delta. Okay, so if you want to use the other notation, so this is the same as x minus x naught square plus y minus y naught square. Okay, and it is the same as this thing. Okay, and similarly for the same epsilon we should be able to find another delta. Okay, so z minus z naught is less than delta. So let's call it delta 1 and let's call it delta 2, because these are two different functions. So these deltas should be in principle different in both cases. Okay, so this is a given fact. So we are allowed to use these facts so whenever we want in this part of the proof. Now what do we want to prove? So we want to prove that the limit of f of z as z approaches to z naught is this complex number. Now to simplify the proof, which we shall see how it will simplify, we should assume this to be epsilon by 2 instead of epsilon. Okay, so let's take them to be epsilon by 2. We will see how it will simplify the proof in our next step. Now, given these statements, now we want to prove the following thing. To prove that f of z minus z naught is less than epsilon whenever z minus z naught is less than delta greater than 0. Okay, so to prove for epsilon greater than 0, there exists delta. In other words, we need to find delta. Okay, so we need to find delta, which is of course a function of epsilon. In other words, it depends on the epsilon. Now we can simplify this notation in the following form. So u minus u naught plus iota v minus v naught less than epsilon whenever this distance z minus z naught is less than epsilon delta. Now we want to find this delta. Find. Now if we take, okay, so take delta to be minimum of the two values of delta 1 and delta 2, then this delta will work. Now let's see how it will work. Okay, so now this u minus u naught plus iota v minus v naught. So we want to prove that this should be less than epsilon. So this is less than or equal to u minus u naught plus v minus v naught, and of course mod of iota, which is equal to 1. So this is equal to u minus u naught plus v minus v naught. Now this u minus u naught is less than epsilon by 2, and this v minus v naught is also less than epsilon by 2. So this becomes epsilon. So this distance is less than epsilon, but under what conditions? So the first statement holds. So this first statement holds when the distance between z minus z naught is less than delta 1. And the second statement holds if the distance between z minus z naught is less than delta 2. Okay, greater than 0, greater than 0. So if we want to use both these facts, that this is less than epsilon by 2 and this is less than epsilon by 2, then we should assume that the distance between z and z naught is less than the minimum of delta 1 and delta 2. So in fact we take our delta to be the minimum of delta and delta 1 and delta 2. So in other words, we can say that for this epsilon we have found a delta which is in fact this delta, and corresponding to this delta the distance between f of z and z naught is less than epsilon. So in this discussion we presented a proof of the relation between the limits of complex valued functions and the limits of real valued functions. This connection is very useful for calculating the limits of complex valued functions. In our further discussion we are going to use this connection, and of course we are going to present some further results about the limits of real valued functions, and of course using this connection we are going to see how it will simplify the calculation of the limits of complex valued functions.